Okay, we're going to get started with the examples. We have four examples, and one that's in particular, we're talking about common Pythagorean triples. Now, Pythagorean triples was part of your vocab, and so you should have written or learned that basically a Pythagorean triple is a set of non-zero whole numbers, a, b, and c, that we use, that satisfy the equation a squared plus b squared is equal to c squared. So your Pythagorean triples, as stated, they satisfy the equation a squared plus b squared is equal to c squared, okay? And here, let me zoom in a little for that so you guys can see it a little better. All right, so some of our common Pythagorean triples, which you're going to get used to seeing, and if you see them, you should know if it's the Pythagorean theorem. The first one is 3, 4, and 5. All right, if you were to plug this into the calculator and you went 3 squared plus 4 squared, you'd get 9 plus 16 is equal to 5 squared, which is 25. 9 plus 16 is equal to 25. So that's one. A second Pythagorean triple that you should get used to seeing and know that you have one is 5, 12, and 13, all right? If you put this into the calculator, you'll get 5 squared, which is 25, plus 12 squared is 144. Together, those equal 169. 13 squared is 169, so it is a common Pythagorean triple. Looking at a couple more, we also have 8, 15, and 17, as well as 7, 24, and 25. All right, so those are like some of our common, let's zoom out, Pythagorean triples. All right, so kind of get those in your head knowing that's what they are. All right, but now let's go look at example 1. Example 1, we want to know what is the length of the hypotenuse of this triangle ABC, okay? So we have our triangle ABC, and I've been using this green to represent my hypotenuse. So from A to C, that's my hypotenuse. From A to B, this is one of my legs. I've been using this pink. And from B to C is my leg number 2, L2. I've been using this blue. All right, so this is my H. Let me get the right colors going on here. I apologize. 24, this is going to be my L2. And for 18, this is going to be equal to my L1, all right? Because we've been using that formula, L1 plus L1 squared plus L2 squared is equal to the hypotenuse squared, all right? So we're going to write that over here. So we want to know what is the length of the hypotenuse. We know what L1 is, we know what L2 is. We're going to plug it into our formula to find out what H is, all right? So we have L1, and it's squared, plus L2, which is squared, is equal to H squared. All right, so let's zoom in a little bit more. All right, so we're going to plug in what we know L1 to be, what L2 is. L1 we know is 18, so I'm going to plug that in. 18 squared plus my L2, which is 24 squared, is equal to, I don't know what H is, so I still am just going to have H squared. All right? So now, 18 squared is equal to 324. So that's what I'm going to put here. 324 plus 24 squared is 576. Is going to be equal to H squared. Adding 324 to 576, we're going to get 900. 900 is equal to H squared. Now we need to solve for h. We have to take the square root because that's the opposite of squaring. So whatever I do to one side, I do to both. And so what happens is that the square and the square root cancel each other, all right? So we're going to end up with this h by itself. But the square root of 900, we need to break it down. And we're going to get it into its simplest radical form, if at all possible. And hopefully we'll get a whole number, all right? So I'm going to just show 900 over here. So the square root of 900. And we're going to use our factor tree, okay? Getting it down to its prime numbers, which makes it up. So we know that 900 is made up of 10 times 90, right? Now 10 can be broken down further to 2 and 5. And 2 and 5 is a prime number. That's as far down as we can go with that one. Now 90, we can make it go down further, which is 9 and 10. 9 can be broken down to 3 times 3. And 10 is 2 and 5. So these are our lowest forms that we can get to. These are our prime numbers. And we're going to put those back underneath the radical, and we're going to group our like numbers together. If we have two of the same, we can pull them out, and it's going to give us the simplest form of this square root of 900, all right? So showing that over here, underneath our square root, we're going to have, I have a 2 and a 2, so I have 2 times 2 times, I have 2 3s, and I have 2 5s. Now, my like terms, I'm going to, or like numbers, I'm going to circle them. I have 2 pairs of 2s, I have 1 pair of 2s, 1 pair of 3s, and 1 pair of 5s. I can bring those outside, so if I have two of the same thing, I can bring in the 1. So I have 2, I'm going to have a 3, and I have a 5, which is going to all be equal to h, because I have nothing left underneath the radical. So 2 times 3 is 6, times 5 is 30, so h is equal to 30. That is what my hypotenuse is. It's 30. All right, that's what I was just writing underneath right there. All right, so that's example 1. Example number 2, right? We want to know what is the value of x, and we're going to express our answer in simplest radical form. So it looks like this one, we're going to probably have our answer that has a radical. You know, it's going to be up underneath that. So let's see what we have here. We have our right triangle. We know it's a right triangle. And we know that our hypotenuse, which I'm going to show in green, is equal to 20. So I'm going to put this h here. And I'm sorry you can see some of my writing on the other side, but I guess my pen was a little dark. And our 8, which is one of my legs, I'm going to call that L1. This is going to be equal to L1. And my x over here, which I don't know what that is. That's what I'm going to have to find. That is going to be my L2. Okay? So we're going to have our L1 squared plus L2 squared is equal to our h squared. We're going to write that over here, all right? So we're going to have L1 squared, and again, I apologize that, I guess I won't use that black pen again. L1 squared plus L2 squared is equal to my h squared. Now, L1 squared, I know it's 8, so I'm going to substitute that in. I have too many pens in my hand. So this is going to be 8 squared plus L2 squared. I don't know what that is, but I know I'm going to put in x. It's going to be my x squared. It's going to be equal to my hypotenuse, which is 20 and I'm going to square it. Okay, now I'm going to zoom in so we can see it a little bit better. So 8 squared is 64, plus, I don't know what my x squared is, so I'm just going to leave it, is equal to 20 squared, which is 400. We're going to get our like terms together, subtract 64. We're going to end up with x squared, because those cancel, is equal to 336. Now to solve for x, I have to take the square root of both sides. The square root and the square cancel, so I'm going to end up with an x. I'm going to determine what my x is equal to by using my factor tree to figure out what 336 breaks down to. So I have 336. 336 is made up of 2 times 168. Now 2 is a prime, so I don't need to break that down any further. 168, that is made up of 2 times 84. Don't have to break the 2 down any further, but I need to break this 84 down further. 84 is made up of 2 times 42. 2 is a prime, so I'm done with that piece, but the 42 I got to break down further, which is 2 times 21. That's a prime. My 21 is going to be broken down to 3 and 7. Okay? So I've broken it down as far as it can go. So I have 2, 2, 2, 2, 3, and 7. All right? Now I'm going to show this over here, because I really don't have a lot of space. So the square root of 336 is equal to, putting it under the square root, I have a 2 times a 2 times a 2 times a 2 times a 3 times a 7. All that is underneath my radical. Well, I have 2 pairs of 2's. I'm going to circle those. So these are going to come outside. I'm going to have a 2 times a 2. And what's left under the radical is the 3 times the 7. So this is going to be 4 times the square root of 21. So that is what my answer is going to be over here. X is equal to 4 times the square root of 21. All right? Okay, let's get over to example 3. Okay, so example 3. We need to know, do the following triangle lengths form right triangles? Let me see. And if so, we need to explain. All right. So we are given these lengths. So I'm going to zoom it back in. I zoomed out so we can see the whole problem. We have 85, 84, and 13. Okay. So 85 is my longest side. So I'm going to make that, or assume it's my hypotenuse. Okay. So I'm going to have 84 and 13 are my legs. So we're going to see if it's going to work out. So I have 84 squared plus 13 squared is equal to 85 squared. So let's see if this works. 84 squared is 7,056 plus 13 squared is 169 is equal to 7,225. 7,056 plus 169 is 7,225, which is going to be equal to 7,225. So yes, this checks off. It is a right triangle. So we can say yes, this is a right triangle because of the converse of the Pythagorean theorem. All right, so it's true because of the converse of the Pythagorean theorem. All right, let's look at the second one here. We have 12, 13, and 14. 14 is my longest side. So we're going to see if this fits the Pythagorean theorem. So we're going to have 12 squared plus 13 squared is equal to 14 squared. All right, we'll zoom in a little. There we go. So we're going to end up with this being 144 plus 169 is equal to 196. 144 plus 169 is 313, and this is 196. So this is not equal. So we're going to have to say no, because the sum of the squares of the smallest sides is not equal. Let's move this over, I'm sorry. Is not equal to the square of the longest side. Okay? So, no, it doesn't fit, all right? It is not a right triangle, and that's the explanation, all right? Okay. Last one for example 3. We have 66, 50, and 18. So we want to know the fits. So 66 is going to be my bigger side. So I'm going to put a box around that. So we're going to have 50 squared plus 18 squared is equal to 66 squared. Well, 50 squared is 2,500 plus 18 squared is 324 is equal to 4,356. These two add up to 24, which is not equal to 4,356, which is basically the same reason as above. Let me zoom out. We're going to have to say no, because the sum of the squares of the smallest side is not equal to the squares. And it looks like my pen is trying to run out of ink. Squares, let me zoom in. Squares of the longest side. Okay? All right, so that's 3. Going to example 4. Example 4. We need to know, do the following triangle sides make acute, obtuse, or right triangles? Now remember, this is dealing with, we looked at the obtuse triangle theorem and the acute angle theorem, all right? So that's what we're gonna be looking at. So what we have is we have our first one, which is, let's zoom in a little, is 6, 11, and 14. So 6, 11, and 14. 14 is my biggest side, so we're going to see what's going to happen. So I have 14 squared. I'm going to take my two smallest sides. I have 6 squared plus 11 squared. All right? Well, 6 squared is 36 plus 121. Together, this equals 157. Well, 14 squared is 196. Well, this is greater than 157. So, since it's greater, and if we go by those two theorems, we know that if my side is greater, then it's going to be an obtuse triangle. So this is an obtuse triangle. All right. So let's look at our second one. We have the square root of 3, square root of 3, and square root of 6. Well, the square root of 6 is my longest side. So we're going to look at that. So remember, if we have the square root of anything and we square it, remember the squares and the square root cancel each other out, okay? So I have also my square root of 3 squared plus my square root of 3 squared, okay? So these cancel out. So what I'm left with is, this is going to be 6. This is 3 plus 3, which is this is 6. So this is equal. So this is a right triangle. All right. Last one. We have, I guess I'll do this in purple, 6, 4, and 5. 6 is my biggest side, longest side. So I'm going to have 6 squared. I'm going to have 4 squared plus 5 squared. 4 squared is 16, 5 squared is 25. This is going to be equal to 41. 6 squared is 36. So this is smaller than 41. So this is going to be an acute triangle. All right. Well, those are your notes, guys. Have a good one. Hope you are behaving.